Hello everyone. In this video, we are going to see the characteristics of DC machine. First, we will see the characteristics of DC motor. There are three characteristics for DC motor. The first characteristic is plotted by taking torque and armature current. So the graph plotted between torque and armature current is the first characteristics. The second characteristic is drawn between the speed and the armature current. And the third one is plotted between the speed and the armature torque, speed at the torque. So these are all the three characteristics for DC motor. The second characteristics, the first characteristic, which is plotted between torque and armature current, it is also called as electrical characteristics. And the characteristic which is plotted between speed and torque, it is also called as mechanical characteristics. Now we are going to see these three characteristics for shunt, series and compound motor. So these equations are used for plotting the characteristics of the DC motor. The first equation is the torque equation. We know that the torque is directly proportional to phi into Ia, where phi is the flux and Ia is the armature current. And the speed is directly proportional to Eb by phi. Eb is the back EMF. Eb can be written as V minus IaRa. So N is directly proportional to V minus IaRa divided by phi. So these three equations will be used for plotting the characteristics of the DC machine. Now we are going to see the characteristics for DC shunt motor. To plot the first characteristics, that is torque versus Ia characteristics, we will be taking the first relation. Torque is directly proportional to phi Ia relation. But for shunt motor, phi is going to be a constant one because the shunt field winding is connected in parallel with the supply voltage, and the variation in the shunt field current will be very, very less. So the flux will be almost constant. So we can consider that the flux will be a constant one, so that the torque will be directly proportional to Ia only, because it is because the flux is going to be a constant one. So when we plot the torque against Ia, since this is going to be a linear relation, we will be getting a linear straight line when we plot the torque against Ia. So as Ia is increasing, torque is going to increase in the linear manner. So this is going to be the torque versus Ia characteristics for shunt motor. Now, to get the second characteristics, that is speed versus Ia characteristics, we need to consider this equation, the second equation. Speed is directly proportional to Eb by phi. Again, phi is going to be a constant one, so we can write that speed is directly proportional to Eb alone. Again, Eb can be substituted as V minus IaRa. So speed is directly proportional to V minus IaRa. So as Ia is going to increase, IaRa is going to increase. So V minus IaRa is going to decrease. So the speed versus Ia characteristic will have a drooping characteristics, which is due to the increase in the value of IaRa. So the next characteristic is speed versus torque characteristics, which is plotted between the speed of the machine and the torque. And we know that torque is directly proportional to Ia. So as Ia is going to increase, torque is going to increase. Torque is going to increase. As torque is going to increase means IaRa, it is going to increase. So therefore, speed versus torque characteristics will be similar to the shape of the speed versus Ia characteristics, because Ia and torque both are proportional to each other. So next, we are going to see the characteristics for series motor. Now, for series motor, to draw the torque versus Ia characteristics, again we are going to take the same relation. Torque is directly proportional to phi Ia, and we know that for series motor, field current, armature current, they are all same. So phi is directly proportional to Ia. Therefore, torque equation can be written as torque is directly proportional to Ia square, and this will be the case till saturation. After saturation, even though the armature current is increasing, the flux will not increase. Flux will become constant. So after saturation, torque will be directly proportional to Ia. So until saturation, we will have this relation, torque is directly proportional to Ia square. So until the saturation point, the characteristic, it is going to be a parabolic characteristics. Once after saturation, torque is directly proportional to Ia only. Therefore, we will be getting the linear characteristics. So this is the torque versus IA characteristics for series motor. Now to plot the characteristics between the speed and the armature current, again we need to take N is directly proportional to EB by phi. For EB can be written as V minus IA into RA plus RAC, and since phi is directly proportional to IA, we can write it as IA. Instead of phi, we can write it as IA here. And if we take RA and RSC value, it is going to be slightly less. It is going to be very less value only. Therefore, we can neglect IA into RA plus RSC, and we can assume that the speed, the change in speed with respect to IA will be more when compared to the change in speed with respect to the numerator. So we can neglect the contribution of the change due to this IA into RA plus RSC, so that we can directly write the speed is inversely proportional to IA alone, because this will not contribute much change. So we can see that the speed is inversely proportional to IA, and hence we can get the characteristics as the hyperbolic characteristics. The characteristic between speed and IA for the series motor will be of this shape. Again, if we plot speed against torque, and since torque is directly proportional to IA square till saturation, and it is going to be proportional to IA after saturation, again the characteristics between N and torque will have similarly will be having a similar shape of this speed versus IA characteristics, because torque and your torque is going to increase as your IA is going to increase. So these are all the characteristics for series motor. Now we can see the characteristics of compound motor. These characteristics of compound motor, they are all the characteristics for cumulative compound, because in practical scenario, we will be using the cumulative compound because differential compound will not be used in practical cases. So the characteristics for compound motor, cumulative compound motor alone are shown here. So the torque versus IA characteristics for cumulative compound motor will be like this, which will be having the combination of the series and the shunt motor characteristics. So torque it is going to have the shape like this. And again, the speed versus IA characteristic will be having this characteristics, wherein the drooping level of the speed with respect to IA will be more when compared to the shunt motor. And again, the speed versus torque characteristics for cumulative compound motor will be having a shape in this manner. So next, we are going to see the characteristics of a DC generator. The DC generator characteristics will be of three different characteristics. The first characteristic is open circuit characteristics, which is also called as magnetization characteristics. So this magnetization characteristics or open circuit characteristics, or it is also no load characteristics, can be plotted between the no load generated EMF and the field current. No load generated EMF is nothing but without any load. If we consider the generated EMF, that EMF is called no load generated EMF. The shape of this characteristic for all types of DC machine will be of same shape. So it is the no load. It is also known as the no load saturation curve. So open circuit characteristic or magnetization characteristics, it is plotted between the no load generated EMF and the field current. The next characteristics will be the internal characteristics. This is plotted by between the generated EMF on the load with the load. With load, we have to take the generated EMF, and it is plotted against the armature current. So if we consider the load, then there will be armature reaction effect. So the actual generated EMF during the load condition will be slightly lesser than the no load EMF, because at no load condition the armature reaction will not be there. So if we plot the generated EMF at a loaded condition against the armature current, we will get the internal characteristics. So this is the internal characteristics. And the third characteristic is the external characteristics, or it is also called as load characteristics, which is plotted between the terminal voltage and the load current. The terminal voltage will be lesser than the generated EMF because the terminal voltage will be the generated EMF minus the resistive drops in the armature. Or if in case of a series machine, it is going to also include the series field winding drop. So if we plot the terminal voltage against the load current, then we will get the external characteristics. Now, these are all the characteristics drawn, the three characteristics drawn for the DC series generator. The first plot is nothing but the no load EMF, which is plotted against the field current. Field current here is nothing but the ISC, that is series field current. So we all know that the field, the flux, actually it is plotted between E0 and ISC. E0, we know that it is directly proportional to phi. So your E will be increasing in a linear fashion until saturation. After that, it is going to be, after saturation, the increase in the phi will be lesser, and after some time it will become constant. So the EMF generator will be increasing until in a linear fashion until saturation. After that, the increase will be will not be of linear fashion. So this is the no load characteristics or open circuit characteristic of the series generator, which is plotted between no load generated EMF and the field current. Now you will be having a concept called residual voltage here, which is the voltage that is generated even when there is no field current. So for that voltage to be generated, we should have some residual magnetism in the generator. So for self-excited generator to for self-excited generators to generate, there should be always a residual magnetism in the pole, which will induce a small residual voltage that will make a small current flow through the field winding, which in turn will increase the induced EMF again, and this process will continue. Will continue, and the increase in the induced EMF will take place. So for a series or shunt generator, that self-excited generator, there should be always a residual magnetism present in the pole. So this is the open circuit characteristics. Now next is the internal characteristics, which is drawn between the generated EMF and under load condition and the armature current. So if we consider the value of this E will be lesser than this E0, because this E is nothing but E0 minus the drop due to armature reaction. So this curve will lie slightly below this curve, since for series generator, ISC, IA and IL all are equal. The shape of the characteristics for internal characteristic will also be same as that of the open circuit characteristics, but it will be lying slightly below this line. And similarly, the terminal voltage against IL, if we plot, again the shape will be similar to these two shapes, but it will lie slightly below the these two characteristics. So this V is nothing but E minus IA into RA plus RAC. So that value is plotted against the load current. So we can combine all these three characteristics, and we can show all these three characteristics. This is the open circuit characteristics, this is the internal characteristics, and this is the load characteristic or the external characteristics, which are all plotted against the ISC, which is also same as IA, which is also same as IN. Because series generator, the field current, armature current, and load current all are same. Now we are going to see the characteristics of DC shunt generator. The first characteristic will be the open circuit characteristic, whose shape will be the same as that of your series generator. The second characteristic is plotted between the generated EMF under loaded condition against IA. So this E will be equal to E naught minus armature reaction, that is drop due to armature reaction. So this point is nothing but the E naught value, which is the voltage generated when it is the generated voltage at IA equal to 0. So as IA is going to increase, so due to the armature reaction, the EMF value, the generated EMF value will be lesser when compared to the no load generated EMF. So it will have a slight drooping characteristics. And the V is nothing but E minus IARA, so which will be lesser, which will lie even below this E versus IA characteristics. So V is equal to V will be equal to E minus IARA. And so if we plot all these three characteristics in the same plane, we will get this is the no load characteristics or the open circuit characteristics. This is the internal characteristics drawn between E and IA. And this is the external characteristics, which is drawn between terminal voltage and the load current. So, so far we have seen the characteristics of DC machine, DC motor, and DC generator. So we have seen the DC characteristics, that is for a motor we have seen three characteristics, torque versus IA characteristics, speed versus IA characteristics, and speed versus torque characteristics. For generator we have seen again three characteristics: open circuit characteristics, external characteristics, and internal characteristics. Thank you.